All right, so we're going to continue our discussion on logarithms, but we're going to do it today in this video kind of on a tangential topic. We will use logarithms in the homework assignment that goes with this video. You'll work with logarithm problems. However, this video focuses on a number, a constant, a mathematical value that is known and is associated with logarithms. So you won't do a lot directly with logarithms, and there won't really be anything in this video that progresses your knowledge of logarithms, with the exception of one piece of notation. But all of this you'll see in later videos as we continue our discussion on logarithm. All of this will tie together, and this actually becomes very, very important as we discuss logarithms. So with that said, this video is about Napier's constant, which is just a number. And we're going to get started by looking at the learning objectives like usual. Okay, so the first thing that we need to know is the symbol and the approximate value of Napier's constant. So again, remember, when we say constant, okay, that just means that this is a number. That's what Napier's constant is. It's just a number. And so we need to know the value and the symbol that represents that number. And we'll talk about why it has a symbol and stuff once we get into the video here. Be familiar with alternate names. I will say this maybe isn't really a learning objective. We will spend a couple minutes talking about alternate names for Napier's constant. In fact, within, especially at the high school level, very, very few people actually call it Napier's constant. It's usually called other things. So we'll spend a second or two talking about this. This is not something that I would test you on, though. So that's not really a learning objective, but it is something that we'll need to talk a little bit about. Now, using Napier's constant, again, this is just a number. So use this particular number as we simplify expressions or solve equations. That's definitely something we'll need to do. And then this is the one piece that connects back to logarithms. Remember, I mentioned in a previous video that there were two shorthand notations associated with logarithms. One of them we learned in the last video, that was for the common logarithm. The other one deals with Napier's constant. So once we know what Napier's constant is here in just a minute, we'll be able to learn that second shorthand notation for logarithms. Okay? All right, so let's get started here with learning objective number one. Just what is Napier's constant? What's its value? What's going on with that? Okay, so a little bit of background for just a second. Okay, a little bit of background. We know, okay, some things that we know. One thing that we know is that there are different kinds of numbers, and some numbers are irrational. Some numbers are irrational. Okay, so when you think about irrational numbers, probably for most people, the first thing that comes to mind is pi. But remember, these are numbers. They cannot be written as a fraction. At least not a fraction that's like a simplified, integer divided by integer type of fraction. Okay, so they can't be written as a fraction. Their decimal go on forever. Okay, so when I expand this out as a decimal, that expansion will never, ever end. And the decimal will not ever have a pattern. At least not a pattern that repeats. Okay, that might seem redundant, a pattern that repeats. A pattern that goes through the whole expansion. There might be a very short pattern in a little tiny part of the expansion, but that pattern always breaks down. It never continues throughout the whole decimal. So when we think about pi, pi is a number that acts this way. So I want to share my screen for just a second and take a look at some information about pi for a minute. Okay, so pi we're familiar with. So Wolfram Alpha, that's a website that we know. And if I just go in and figure out pi, Wolfram Alpha says, okay, so here's, it understood my input to be pi. And we can see there's this decimal. We usually memorize 3.14, but obviously it keeps going. In fact, it keeps going for a really long time. And we could just sit here and I'm not sure how many digits Wolfram Alpha will go to, but obviously it goes to a lot and it keeps going. Okay, so this is the kind of thing. And as we look at all these digits in here, there's not a consistent pattern that repeats itself over and over and over again. You can see, like, for example, right here, I can't highlight it. There's a little bit of a pattern for a minute. It goes 9, 9, 9. So you have this 9 repeating, but that's only there for just a very short time. That doesn't consistently hold, okay? So this is the situation where we're dealing with irrational numbers, all right? Now, there are other types of irrational numbers, but because of the fact that they have this ongoing expansion that doesn't repeat, we always represent irrational numbers using, or I should say common irrational numbers. Common irrational numbers are represented symbolically. Okay, so I'm going to say with symbols. Okay, with symbols, symbolically. So again, the most common one is pi. And so we don't try to write out this whole great big long decimal expression for pi. What we do with pi is we just write down the Greek letter pi. So for example, we write down the Greek letter pi. Okay. Another example, square root of 2 turns out to be a very common thing, especially if you're studying trigonometry and things of that sort. So we don't try to write out the decimal expansion for square root of 2. We just simply write this symbol, square root of 2, and we just write it like that. There's another number that's very, very common. I pronounce it as phi. Some people pronounce it as phi. But that's a very common one. Particularly, this is a number that occurs in a lot of architecture and a lot of patterns that occur in nature and stuff. This might be something that you may have heard of if you ever watch math videos or things like that. It's called the golden ratio, it's also known as. But these are things, this is a decimal that goes forever, but we just use a Greek letter to represent that decimal. Okay, Napier's constant is like this. Napier's constant is an irrational number. Also, okay, Napier's constant is also an irrational number. And so we have this same problem. It's a decimal that goes forever and ever and ever. And so we have to have some symbol that represents it. Now, the symbol that was chosen to represent this is the letter E. So this, as far as your short math career so far, this might be the first math number that uses an English letter to represent it. Or maybe English is wrong because there's other languages that have E in it also, but it's not Greek though. It's not a Greek letter like pi is, okay? So, so that's a little different. So mathematically speaking, every time we see the letter E, the first thing we should think of is Napier's constant. So anytime I'm working with a mathematical equation, and the equation has an E in it, the first thing I should think of is Napier's constant. Now, there are some exceptions. There are times in math where we use the letter E and it represents other things. But I will say, because the mathematical community associates this letter with this number, almost always when you see this letter in a math equation or expression, it almost always represents this number. Okay, so what is this number? Well, let's go back to Wolfram alpha here for just a second. And we can do the exact same thing we did with pi, except let's type in Napier's constant instead. There it is, Napier's constant. All right. So Napier's constant, you can see it interprets that as being E. That's my symbol for it, is the letter E. And here's my decimal approximation. Just like pi, it goes on and on and on and on, okay? So all we're gonna need to know for our class, kind of like pi, is just the first couple digits, okay? Now, me personally, if you only do the first 3 digits, like with pi, we would do 3.14. Well, the problem with this is the next number is an 8, which would make it round off. So personally, I remember the first 4 digits with this, 2.718, and that's what I remember. Okay, so this is Napier's constant, right? Now, I did mention, well, let's write this down, okay? So E is approximately equal to 2.718, okay? So that's what I remember. It does keep going. In fact, the first part here continues with a pattern. It looks like there's a pattern as you keep going here, but then after this, this next 8 right here, then it breaks down, okay? But again, it looks like there's a pattern. It's just that pattern doesn't continue forever. So what I remember is the 2.718, and that's what I use, all right? So this is what Napier's constant is. Now, I did mention that there are other names for Napier's constant. So Napier is the name that I prefer. Napier is the mathematician and astronomer who's given credit for having invented logarithms. But if you go like to Wikipedia, Wikipedia will call this Euler's constant, which personally, for a lot of reasons, I have a huge problem with. This is one of those spots where I think Wikipedia is wrong. Some people would disagree with me, okay? It's just often just called E, just like this number we just call pi because that's the Greek letter pi. This number we often just call E, okay? So I'm going to say usually called E. That's usually what we call it, okay? It's also sometimes called the natural number. Now, there's a small problem with that name because we learned a set of numbers that are called the set of natural numbers, and that's different. In fact, this is not even in the set of natural numbers. Remember, natural numbers are numbers that don't have decimals, and they're not negative, and they're greater than 0. And this is not a natural number. So this name is also problematic. I will say personally, this is what I will use the most in our class. And that's probably what your future math teachers will use the most also, okay? So just so you're comfortable with that idea. Now, the reason why we sometimes call it the natural number, I'm going to skip for just a second ahead to our learning objective number 4, which was on shorthand notation for logarithms, okay? Because sometimes it's called the natural number. And the reason for that is because in shorthand notation, if I put E as the base of my logarithm, and again, it doesn't matter what X and Y, I'm just focusing on this right here. When the logarithm has a base, whoops, base has an S in it, base that's equal to E, it's called the natural logarithm. Okay, the natural log, the natural log. So remember in our last video, we said if it was base 10, that's the common logarithm. When it's base E, it's the natural logarithm. Now, common logarithm was not vocabulary that I expect you to know. You might hear me say that on occasion, but there'll never be a test that says, hey, what's the common logarithm of this or anything like that. Natural logarithm, on the other hand, is vocabulary you need to know. This you will hear again and again and again. You need to know the phrase natural logarithm, and you need to know that that means its base is E. And just like we had with the common logarithm, there is a shorthand notation for the natural logarithm. So if I have log base E of x equal to y, if that's what I have, log base E of x equal to y, then the shorthand notation for the natural logarithm is ln. ln. So ln stands for the natural logarithm. Why don't they make it NL? I don't know. But ln, that's our natural logarithm, okay? So anytime you see ln, that always refers to the natural logarithm. In fact, I will say, me personally, just because of the way I was trained by my previous math teachers, I usually write ln using cursive letters. So I usually write it like that, ln. That is the same thing as log base E, okay? So this and this, they mean the same thing. Okay, those two things mean the same thing. Log base E, or the natural logarithm, is known as the natural logarithm, and we use the symbol ln, okay? Now, with all that said, I think we're ready to start using this in equations and in expressions. Okay, so the first thing I want to point out to you is obviously we can do these problems on Wolfram Alpha. You saw that, right? We could just type in fact, let me share my screen for just a second and go back to Wolfram Alpha just to make sure we're clear with this. Okay, but in Wolfram Alpha, obviously you can type in like, E plus 2, and you can see it understands what we're doing here. It writes that as our decimal. 2.7 plus 2 would be 4.7, right? We can also do like natural log of 5, okay? It understands that, okay? It gives me this weird funky decimal because my base is a weird funky decimal. So, but it can do that, all right? So Wolfram Alpha can handle this sort of stuff, but this sort of stuff is also on my calculator, okay? So remember, if I ever wanted to type pi on my calculator, I had to push the second button and then the caret. That's how I got pi. So if I push second caret, that gives me pi, and we can get it that way. Well, E is the same thing, but it's not the caret, it's the divide button. So if I push second divide, that gives me E. And if I push enter, there's Napier's constant, okay? So again, I can do any sort of arithmetic. So if I want to do E plus 2, there's my, 2 plus 2.7 plus 2 would be 4.7, right? So there's my answer. So I can work with Napier's constant on a calculator. I can also work out with it on Wolfram Alpha and other places as well. Okay, so that takes care of learning objectives 1, 2, 3, and 4. I think we've covered all of them. Know the symbol and approximate value of Napier's constant. So the symbol is E. The approximate value is 2.718. Use Napier's constant in expressions and equations. So for today, we're going to do the exact same thing we did in previous videos. We're either going to switch from log notation to exponent notation or back again. And we're also going to now do some problems on our calculator where we get decimal approximations. And then last but not least, know the shorthand notation for the logarithm, and that's ln. That's our shorthand notation. All right, so thanks for watching. Have a good one.